Hello, hello, hello friends. So this will be a very quick revision video on quantum chemistry. Quantum chemistry. So as we know, we'll start with some basic concepts that psi, as we know, is the amplitude, p is probability, which is equals to psi star d tau over the integral, which can be from a to b, where a and b can be any number, and d tau is equals to r square dr sine theta d theta d phi. This is the polar coordinates, which is mainly used in quantum chemistry, especially for hydrogen atom. For particles in a box and SHO, normally the Cartesian coordinates are only used. So we'll start with the first model, that is particle in a box. We'll study about three models: particle in a box, simple harmonic oscillator, and hydrogen atom. There are also some other models like the rotor, from which we'll see one or two questions, but they are not that important. So particle in a box is mainly what it says, that it is a particle which is in a box and we calculate its movement. So the particle which is taken actually is an electron and we calculate its probability in different locations. And the wave function psi actually gives us the nature of the electron, because in quantum mechanics we know that electron is not just a particle but is also a wave, which is comes with a wave particle duality. So the psi for this electron is given by root of 2 by L sine of n pi x by L, where L is our length of the box. And this psi changes on different conditions, of which we will learn later. And so these are some small tricks, that if the box is from 0 to L, and if we can make the box in 4 parts, such that this is L by 4, this is 3L by 4, this is L by 2, then the probability of the particle within L by 4 to 3L by 4 becomes 82%. And the probability from 0 to L by 4 is 9%. And the other part is also again 9%. Okay, so we have the box in 1, 2, 3, 4. We have the box in 4 parts. Okay, and what do we do? We have like if equally divided also, like this L by 2, then this will be L by 4, this will be 3L by 4. The middle portion will be 82%, the side portions will be 8% or 9% each, right? Similarly, if we divide the box in 3 portions, so we will have 2 lines, and this will be L by 3 and this will be 2L by 3. Then the middle percentage will be 60% and the side portions will be 20% each. This is a probability. This is some easy techniques if it's given in MCQs. And we also have the eigenvalue equation, expectation value, which is very basic. This is an operator which operates on psi to give us a small a, and the small a is called the eigenvalue. This psi is called the eigenfunction. And our expectation value, suppose for maybe for any operator for anything, so the expected value of m is equals to psi of m psi star d tau psi star d tau, where psi star normalized will be equal to 1. And now we'll come to some results of particles in a box. So the average of x is equals to L by 2 because the whole particle is from 0 to L, so the average has to be L by 2. And the average of momentum in the x direction is equal to 0. This result is actually true not only for particles in a box but also for SHO and for hydrogen atom also. Most probably I have to check that the average of the momentum in the x direction is equal to 0. And the uncertainty in the position of x is given by root of x squared minus x whole square, where this represents average. So your the trick to remember this is that first the square comes inside and then it goes outside. So the first we do the square of x on the inside and then on the outside. Okay. And normally by Heisenberg's uncertainty principle we know that del x del px is more than equals to h cross by 2. And we also know that our Hamiltonian is equals to this total energy. It will be equal to the kinetic energy plus the potential energy. Kinetic energy is pretty much the same for all the molecules. We can find out from momentum only, because from momentum we can get kinetic energy. Potential energy is constant or has a fixed value for all the different systems. So V is equals to for box and rigid rotor. It is equals to half kx square for SHO, and it is equals to minus E square by R for hydrogen atom, or sometimes given by minus E square by 4 pi epsilon R. And the kinetic energy is given by something like this, d square dx square, because kinetic energy is equals to px square by 2m. Okay. Now we'll see some different wave functions for our particle in a box. The wave function will depend on two mainly things. One is a length, which dictates it, and one is your quantum number n. So as in the case for a 0 to L box, we actually had the wave function root of 2 by L sine of n pi x by L, and the energy of this was given by n square by x square by 8 ml square. But such is not the case when we actually have the box from L to 2L or minus L to L. Over here the total length is 2L. Sorry, 0 to 2L minus L to L. Also, its total length is 2L. So psi will be equals to root of 1 by 2L sine of n pi x by 2L. And in these cases, also the energy will change n square h square by 8m 2L whole square. So the only the L is changing by 2L. And in these cases, when we have from minus to positive, there can be two cases. One is when n is even, and one is when n is odd. When n is even, it will have a sine function. When n is odd, it will have a cos function. So this is whole length will be psi equals to root of 2 by L sine of n pi x by 2L. This will be psi equals to root 2 by 2L cos of n pi x by 2L. So as in n is equals to odd, as in n equals to 1, n equals to 1, so n equals to 2. And The trick to remember this is that we can think of environmental signs, as in the event and the sign part comes one after the other. So it will be environmental signs in that perspective. Okay, so now we'll look into 2D boxes and 3D boxes. So in 2D box and 3D box, so normally what happens is your energy is additive, okay, but your wave function is actually multiplicative. Sorry, this will be for 3D. For 2D it will be psi x, psi y. So nothing much is asked about from 2D boxes and 3D boxes. The only thing you know about is degeneracy. That there can be many states with this, the same energy, but they are different states. As in, your in 2D box you can think of like 1, 2 and 2, 1 state. They are two different states. They are degen. They have the same energy, right? But they are like they're two states of the same energy, but have different. But they're different states. They are not the same state, right? Similarly, you can have it also in your yeah 3D boxes and all those things, right? And see the length for the x and y and z are different, so you can write the equation. This is the original form of the equation. You can write it. So normally energy was given by what? M squared by h squared by 8 ml squared. Now we are saying that is a 3D box, so it has Lx, Ly, Lz, and all the three lengths are different. So we can write the formula of energy then as Ly squared plus mz squared plus Lz squared into 8 squared by 8 ml. Sorry, 8 m. Right? That's it. So you understood the point. That's mainly of it. And now we come to some aspects of wave function. See, the particle that is in the box is actually traveling in the form of wave, right? So suppose the wave is like this. Okay, is for your n equals to 2, n is equals to n equals to 1. So n equals to 1, the node is given by n minus 1. So n equals to 0. There are no nodes for the here. Has to be one node. Node is equals to n minus 1, so node has to be 1. So here is the node. So like similarly, you have to draw the terminals. Now the length of this given by length of the wave is given length is equals to n lambda by 2. Right, where lambda is the wavelength of the wave. Or you can remember it as n lambda equals to 2. Okay. Now that is like I have said a lot of things about particles in a box. Now I'll say things about your hydrogen atom. So let me use a different pen. Hydrogen atom. Okay, hydrogen atom is not only hydrogen, but it can also hydrogen-like complexes like Li 2 plus, helium plus, similar like Be3 plus, right? And you know the gamma function is very important. The gamma function integral that we talk about a lot of times. That is can be given like r from is from 0 to infinity first of all. R to the power n e to the power minus alpha r dr is equals to, so this n is important as comes like n, it's like it's n plus 1 gamma function divided by alpha to the power n plus 1. Okay, so you see the factors over here is from 0 to infinity and integral. So there can be any constant which is like r to the power n, which is being like integrated and into e to the power minus alpha r, and it has to be like n plus 1 gamma function divided by alpha to the power n plus 1. So n plus 1 gamma function is actually nothing but the n factorial. Okay, so from here you can get, and in, as I told you before, like in hydrogen atom we use our Cartesian coordinate, not a Cartesian coordinates but a polar coordinates. So we have r from 0 to infinity, we have theta from 0 to pi, and we have phi from 0 to 2 pi. So remember the ranges, like phi is from 0 to pi, theta is from 0 to pi, and r is from 0 to infinity. Integral is this. Remember the average value of this is actually asked in questions or sometimes, but the average value of R is 3 by 2 A0. Okay, and over here also again I said that the P R is equals to 0, as was the case also in your this thing. What I said, this was the case in your particle in a box, and this is also the case in your SI. Now there is also a fun, like this is actually for hydrogen atom. Suppose you have given for like to find this average of R for a like a non-hydrogen atom or for some other compound. So you have to, there's a formula for this, and the formula is this. It is n square A0 by Z into 1 plus half into 1 minus L into L plus 1 by 2. Okay, it's n square A0 by Z into 1 plus half, and half, like the half is multiplied in brackets into 1 minus L into L plus 1 by Z by n square, sorry, by n square. So I know it's a very big formula, tough to remember, but if you're suppose given to find the like average of radial distance or something like that for 2p, so for this n is equal to 2, L is equals to 1, so just put n equals to 2 and L equals to 1, you get the answer. For like hydrogen it is Z equals to 1, for helium Z equals to 2, and so similarly you can put it for whatever molecule they give, right? Yeah, it's not an easy thing to remember actually, but what to do, that is what it is actually. So maybe if suppose for any s orbital it's given, so then your L equal to P equal to 0, right? Okay, now I'll talk about a bit more about the Cartesian and polar coordinates. So your x is equals to r sine theta cos phi, y is equals to r sine theta sin phi, z is equals to r cos theta. Okay, and now let me talk about the energy of the hydrogen atom. Energy. Okay, that is too bright, isn't it? So let me just rub this bright portion out. Done, 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 done. Energy. So the energy for the hydrogen atom is given in this form, that energy E is equals to minus 13.6 Z square N square electron volt. Okay, minus 13.6 Z square N by N square. So it's also written that energy is proportional to Z square by N square, and it is equals to minus 13.6 Z square N square by N square electron volt. Or it can be also given in the form of your Rydberg constant, okay, minus RHC, which is Planck constant, and then speed of light, Z square by N square. So actually Rydberg constant into H into C is actually given 13.6 in electron volt, right? And yeah, so Z is your atomic number, N is your quantum number. So depending on that, you have to put values and get the answer. So many times it asks like for the first excited state, what will be the value? So for ground state, if you take it as n equals to 1, then for first excited state it will be like 2 square, right? So it will be minus 13.6 by 4 equals to minus 3.4 electron volt, something like that. That is how it's done. Okay, And now we'll talk about a bit of angular momentum. So angular momentum L is equals to L square equals to L into L plus 1 into H cut square. And this is a general formula. So L square is equal to Lx square plus Ly square plus Lz square. Right? And your Lz is equals to mh cross, where m is a magnetic quantum number. Your radial nodes is given by n minus L minus 1. Your angular nodes is given by L. Total nodes is the addition of this, which is n minus 1. Now we'll talk about SHO. We take this pen, okay, blue pen. Let's see how the blue works. Blue. हाँ चलेगा आज SHO. So for SHO, some results are the average of x equals 0, the average of px is equal to 0. So average of px is equal to 0 for SHO hydrogen atom as well as your this thing, particle in a box. Remember this integral which will be used in your this thing. What do you say? What's the name of this thing? Perturbation theory. This integral will be used. So see the difference between this integral and the previous gamma function. One is the limits. In gamma function, limit was from 0 to infinity. Now limits are from minus infinity to plus infinity. And in gamma function, it was like e to the power minus alpha x. In SHO, this is e to the power minus beta x square. So this is equals to 0 if n is equals to odd, and this is equals to n plus 1 by 2 gamma divided by beta to the power n plus 1 by 2. This is for n equals to even. And remember this fact that n plus 1 gamma function is equals to n factorial. Now we come to the energy of SHO. So the energy of SHO, so for like one dimensional SHO, energy will equals to n plus half H. For a two dimensional SHO, E is equal to nx plus ny plus 1. So half plus half is 1 into H. For a three dimensional, it will be nx plus ny plus 3 by 2. As half plus half plus half is 3 H. And your degeneracy G is equals to n plus 1 into n plus 2 by that is more or less it of SHO. And so those were the basics of quantum chemistry. Now what I will do is will be looking into some of the approximation methods. Okay, some methods to approximate like the variational method, the perturbation theory, and your Huckel molecular orbital theory as well. Also look into Slater's determinant, which is also very important. Okay, but before going into that, I'll just tell you one more important thing about hydrogen atom. Sometimes what they do is they give a wave function, okay, and they say like for the wave function you have to say if it's from which orbital or it is from what place or whatever, right? So I'll just tell you a trick of doing that. Okay, so normally the wave function for hydrogen atom is actually given in this form. Suppose 1s is given like there are some constants involved and e to the power minus of 2r divided by a0. This n part is actually your uh, quantum number, like your principal quantum number, right? So this is the trick. So suppose I'm giving you this wave function, 4 by 27 root 2, 2 by 3 to the power half, zr square by a0 whole square e to the power is 2r by 3a0. So it is from like you have to say that it is from which quantum number. The quantum number for this will be your n equals to 3 because this part is 3. Okay, so that was for the quantum number. And now for your azimuthal quantum, sorry, for your azimuthal quantum number is L, right? So for that what you have to do is you have to look at the term that is being multiplied to the exponential. Okay, the terms that are being multiplied to the exponential and see the lowest power of r. The lowest power of r uh, is your azimuthal quantum number. So over here, so this actually z square, not this. Over here, the lowest power of r is your r square. This was a0. Okay, so over here it's r square. So 2 is the azimuth L equals to 2, and L equals to 2 means that it is d, right? So it is 3d orbital. Similarly, I will tell you one more, give you one more example, and you have to say uh, the answer. Okay. So suppose I have this. 2 3 by a0 half 27 minus 18zr by a0 plus 2z squared r squared a0 squared into e to the power minus 2r by 3a0. So we have to say the orbital from which quantum number and azimuthal quantum number. So as we know that azimuthal quantum number will be this 3, so n equals to 3. What will be L? You might be tempted to say the lowest power of R is your 27, so R is equals to 1. So you'll say, but that's wrong because the 27 also. 27 is like R to the power 0, and we know that if L is equal to 0, it will be S, and that is what it is. It is a 3s orbital. So that is how it's done. Okay. So these were mainly the parts of it, and now we'll go to the approximation methods that are involved with all these things. But before I go there, I'll just take a small break and then I'll be back. Where's my phone? Okay. we'll look at what it is called the approximation methods. Mhm. Take the red pens. So, friends, I'm back. It's me. I'm back. So, friends, do you listen to gospel songs? Like, can you sing your gospel song? You are beautiful beyond description, too marvelous for words, too wonderful for comprehension. Like nothing ever seen or heard. Who can grasp your infinite wisdom? Who can fathom the depths of your love? You are beautiful beyond description, majesty enthroned above, and I stand in awe of you. I stand in awe of you. Holy God, to whom all praise is due, I stand in awe of you.
Okay, friends, so now we'll study our approximation methods.
And now we'll talk about variational theorem. It's a very quick video, okay? Very quick video on variational theorem. So what we do in variational theorem is that we take a trial function. Okay, trial function, what has to be the properties of trial function is that the energy of the trial function has to be more than the energy of the original function. Okay, that is it. That is the main thing that we know. So the energy of the trial function has to be more than the energy of the original function. So we'll learn about this video in the next class. Okay. So let me end the live stream over here as it is. I was speaking a lot of gibberish in the end. So I hope you were not bored. I don't think you are bored, right? Should be bored. Bye, friends.